What if somewhere, on a distant icy moon, life has found a way to thrive? Today, we dive deep into new NASA experiments suggesting that the moons Europa and Enceladus might not just harbor vast oceans beneath their frozen crusts, but could also preserve complex organic molecules like amino acids just below their icy surfaces. This video explores the intricate science behind these findings and why they could be a turning point in our journey to find life beyond Earth. So without further ado, let's get started. In new NASA groundbreaking experiments, scientists designed a simulation to replicate the extreme conditions found on Europa and Enceladus, focusing particularly on radiolysis, which is the breakdown of molecules under radiation. The simulation chamber was cooled to a frigid -321 degrees Fahrenheit, and scientists exposed amino acids to gamma rays, a type of radiation common in the outer solar system. This setup mimicked the icy, radiation-soaked environments of these moons in detail. The results were astonishing. Not only did amino acids survive, but they also did so at surprisingly shallow depths. For Europa, amino acids proved resilient up to 20 centimeters beneath the icy surface, especially in areas protected from frequent meteor impacts. Enceladus showed an even more favorable outcome, with vital molecules surviving just a few millimeters below the surface. These results mark a significant shift in how we approach space exploration and the search for extraterrestrial life. The fact that we don't need to dig deep makes these missions less complex and less disruptive, enhancing the practicality of exploring these distant moons in the future. Furthermore, the deeper our understanding of these elements and the extreme conditions they endure, the better scientists can predict potential biosignatures of life. Additionally, amino acids, the fundamental building blocks of life, are crucial for constructing proteins that perform myriad biological functions. These molecules could suggest the presence of life, either past or present. Also, their presence close to the surface would make exploration missions simpler and less invasive. This helps reduce the risk of contaminating these celestial bodies, which is vital for adhering to planetary protection protocols. So, if life's fundamental building blocks can withstand the harsh conditions of these two moons, it raises a broader question. What other secrets might these icy worlds hold beneath their frosty exteriors? So the big question is, what if we discovered life on Europa or Enceladus? What forms might it take in these alien realms? The life that could exist on these moons would need to be extraordinarily resilient, evolving in ways that Earth organisms have never had to. In the dark, frigid, and high-pressure environments of subsurface oceans, hypothetical life forms might rely on chemosynthesis, using chemicals rather than sunlight for energy. These organisms could have developed unique metabolic pathways to survive and even thrive in their harsh surroundings, potentially resembling nothing we've encountered before. Theoretical models suggest that life forms in these environments might be vastly different from those on Earth. Adapted to complete darkness, these organisms might lack eyes or have developed specialized sensing organs to navigate and find food. Their biochemistry could be adapted to utilize the saline, mineral-rich waters, turning what would be toxic to most Earth life into vital energy sources. Recent experiments have provided pivotal data to better understand how amino acids can survive in these extreme conditions. Scientists have found that bacterial cellular material may protect amino acids from reactive compounds produced by ionizing radiation, which changes molecules either by breaking their chemical bonds directly or indirectly, creating destructive compounds nearby. This suggested that microbial life forms could uniquely shield crucial life-building amino acids from harsh environmental factors on these two moons. Moreover, these studies have established radiolysis constants, rates at which amino acids break down due to radiation. Utilizing these constants, researchers have calculated the necessary drilling depths and specific locations where these specific elements are most likely to survive the radiolytic destruction on the icy moons. This marks a significant advancement in astrobiology, as it's the first time such experiments have applied lower radiation doses that don't fully break apart the amino acids, preserving their integrity for scientific analysis. It's also the first to evaluate how well these compounds can survive in simulated conditions of these two moons, including their interaction with dust, which could further complicate their detection and analysis. Astronomers plan upcoming missions to these two moons, but how will these missions be conducted? Will they simply take pictures, or will they collect samples? The answer is both. These future missions, equipped with the latest technology, are designed to undertake extensive orbital observations and land-based explorations. Notably, the Europa Clipper mission, planned for the early to mid-2020s, will perform detailed observations from orbit, capturing high-resolution images, mapping surface features, and analyzing the compositions of Europa's icy exterior. The missions will use robotic landers designed to handle the extreme conditions of the moons, exploring their surfaces directly, which will be equipped to analyze soil, ice, and materials beneath the surface to search for signs of life, like amino acids. It's crucial that these landers are built to protect their instruments from intense radiation and to work at the depths where signs of life are most likely to be found. Additionally, some planned missions, such as the Enceladus Orbolander concept by Johns Hopkins University, will combine orbiter and lander functions. This design would enable direct collection of samples from Enceladus's dramatic plumes and potential hydrothermal vents, which could offer the warmth, nutrients, and energy that are essential for supporting life. Learning from past missions such as Voyager 1 and 2 and the Galileo spacecraft, which have provided invaluable data about the moon's magnetic fields, surface compositions, and subsurface oceans, is vital. These historical insights are crucial for designing new spacecraft that can survive and operate in the harsh environments of these distant moons. Voyager 1 and 2 expanded on the discoveries of the Pioneer missions by providing detailed images and data on the gas giants and their moons. Voyager 2, in particular, is famous for its flybys of Jupiter, Saturn, Uranus, and Neptune, offering the first detailed glimpses of the moons of these planets, including the icy surfaces and geysers of Enceladus, and confirming the existence of complex geological histories. The Galileo spacecraft, specifically designed to study Jupiter and its moons, spent several years orbiting the gas giant, delivering detailed pictures and data that revolutionized our understanding of Europa and its potential subsurface ocean. Galileo's discoveries of apparent water plumes and the seemingly young, icy surface of Europa have significantly influenced the scientific strategies for investigating the potential habitability of this moon. The insights gained from these missions are critical for designing spacecraft that can operate in the extreme radiation, vacuum, and temperature conditions of Jupiter's and Saturn's moons. Thank you for joining me on this journey through one of the most exciting frontiers in science today. As we continue to push the boundaries of what is possible, let us move forward with a sense of wonder and a commitment to responsible exploration. Keep watching, keep wondering, and, most importantly, keep exploring.